Yesterday we introduced the idea of the cathode ray tube and how that led Thomson in 1897 to discover the electron. The cathode ray tube in its most basic form is an evacuated glass tube. There's no air inside this glass tube. There's two electrodes, one electrode over here on the left-hand side, which is a negative electrode, and one electrode over here partway through towards the right-hand side, which is a positive electrode. Which one do we call the negative electrode, the cathode or the anode? The cathode, which seems a little bit odd to those of us who take chemistry, but okay, we make do with that. The positive terminal would be the anode here. Now we know now that if there's a big enough potential difference across this battery, then we're going to get electrons leaving the cathode going towards the anode. At the time, 1897, we knew that something was leaving the cathode going toward the anode. We just didn't know what they were. Okay, we called them cathode rays, these mysterious rays that leave the cathode, go toward the anode, and then skip through the hole in the anode, go over here and hit this screen. Thomson wanted to find out what these mysterious cathode rays were. So he introduced over here on the right-hand side a magnetic field. That magnetic field directed into the page here would cause, by the hand rule for deflection, thumb, fingers, palm points downward, right? It would cause these particles to be deflected downwards. That told Thomson that these particles must be negatively charged particles. Now, it didn't tell him anything about the subatomic nature of these negatively charged particles, but it did tell him that they're not electromagnetic radiation. It's not just light that's traveling from the cathode to the anode. It's some kind of particle, and it's some kind of charged particle, negatively charged particle. Well, he wanted to go a step further from there. He wanted to determine some more properties of these particles beyond the basic negative charge. So he did what we did back in our magnetism unit. He set Fc equal to Fm, the centripetal force equal to the magnetic force, because these particles, these somewhat less mysterious, but still somewhat mysterious, negatively charged particles are going in a circle caused by a magnetic force. mv squared over r is equal to qvb. V's cancel. We're left with mv over r equals q times b. It's all great. The only problem is here, he didn't know what some of the variables were. In fact, he didn't know what a lot of the variables were. He did know what r was because he could tell where the electrons hit the screen. We know where they hit the screen because it caused this phosphorescent screen to glow. He knew where they hit the screen. He could determine from that the radius of the path of these mysterious negatively charged particles. He also knew what the magnetic field was because he introduced the magnetic field, so that was an easy one. He didn't know what M was. He didn't know what V was. He didn't know what Q was. He's got two variables. He doesn't know three of them. So then he decides he's going to do something else here. He introduces over here, somewhere in the middle, another magnetic field. This magnetic field would have the same effect as the first one that we introduced. It would cause the particles to bend downwards. But at the same time as he introduces that magnetic field, he introduces an electric field caused by two charged parallel plates. This electric field would have the opposite effect. If the magnetic field causes the negative particles to be deflected downwards, then the electric force would cause the particles to be deflected upwards. Some of those particles are going to be going too fast. Some of the particles are going to be going too slow. And some of those particles will either deflect upwards or downwards as a result of the speed that's not just right. But some of the particles are going just the right speed so that the magnetic force that acts downward ends up being equal to the electric force that acts upward. Those are the ones we care about because those are the particles that go straight through and then go into this third chamber over here straight on. Okay, those are the ones that we care about. We don't care about the ones that deflect upwards or downwards. Okay, we care about the ones that go straight through. We care about the ones for which Fe is equal to Fm. We see QE is equal to QVB. Okay, Q's cancel. V is equal to E over B. So the speed of these particles, the ones that have gone straight through, is equal to the electric field over the magnetic field strength. Now, Thomson knew what electric field was. He knew what magnetic field was. He was able to calculate V. He took the value of V there and put it into this equation because, of course, the ones that entered that third chamber were the ones that had that speed. Now, he still doesn't know what m is, still doesn't know what q is, but from there he derived an equation not for the charge, not for the mass, but rather the charge to mass ratio. And he does that by taking the m over by dividing, and the b over by dividing. So m goes down, b goes down, and we're left with q over m is equal to v over b times r. The charge to mass ratio. What did he find about that charge to mass ratio? What was special about that number that he found? It was really big. Its value was 1.76 times 10 to the 11 coulombs per kilogram. That was bigger than any other charge to mass ratio ever found. What does that tell him about the mass? It doesn't give him an exact value for the mass, right? But it does tell him that the mass has to be really, really small. If the charge to mass ratio is big, the mass has to be small. In fact, that mass would have to be smaller than any other mass ever found. And if that's the case, then that mass has to be a subatomic mass. It has to be smaller than the mass of an atom. Okay, we've just discovered not only a negatively charged particle, but a negatively charged subatomic particle, the electron. And then, of course, from there, Thomson went on to that plum pudding model of the atom that you guys learned about in chemistry and in Science 10. Remember the electrons floating around inside the sea of positive charge? You guys remember that? If you don't remember that, that's all his model of the atom was. The electrons floating around in a sea of positive charge. It's kind of like go to Vancouver in the summertime and you see all these sailboats in the harbor. Okay, the sailboats are the electrons just floating around randomly in this sea of positive charge. The water would represent the positive, okay, the sea of positive charge. All right, we had 10 questions last night for homework. 9 questions, sorry. Yeah, 9 questions. We scratched number 2, right? Any issues with those 9 questions on page 760? Catherine? That's 3. That's right. Yeah. I'm thinking we're probably going to need 10 too, do we? Okay, let's take a look at those ones here. 3 goes quick for us. What experimental results led Thomson to conclude that all cathode rays consist of identical particles? Don't overlook the obvious on this. Okay. Yeah, in the end, all these particles ended up being deflected the same way, and they ended up having the same charge to mass ratio. Done. 4a, a beam of electrons enters a vacuum chamber that has 100 kilonewton per coulomb electric field and a certain magnetic field. Sketch an orientation of electric and magnetic fields that will let the electrons pass undeflected through the chamber. So this is a velocity selection chamber, right? We don't have to solve anything here until question B, but for question A that you guys asked me to solve for, there's no mathematics involved in it. It's just an orientation of the electric and magnetic fields that will cause the electrons to be undeflected. If that's the case, we need these forces to balance. We need one force upward, one force downward. If the electrons are going this way, and we have a magnetic field, as represented by these X's, into the page, what direction will the magnetic force be on these particles? Thumb, fingers, palm points, downward. So the magnetic force would be downwards. Well, we need an electric force upwards. What direction of electric field do we have to have in order to have an electric force upwards on this negatively charged particle? Well, if we introduce a couple parallel plates, what plate would this have to be? Positive or negative? Positive. That would actually cause an electric field downward, but the electric force would be upwards. You could reverse those as well. You could have the magnetic field out on the page, but if you did that, the electric field would have to be opposite as well, and the top plate would have to be negative instead of positive. Question B, we won't go through that because you didn't ask it, but I'll just real quickly tell you what you would do. You want to find the speed. It's a velocity selection chamber. Fe equals Fm. QE equals QVB. Solve for V. Seven, Use the appropriate hand rule to determine the direction of the magnetic field in question 6 if protons rotate counterclockwise in the same plane as this page. If protons rotate counterclockwise. So here's positive particles going like this, counterclockwise. We're going to use a right-hand rule for deflection here. Thumb in the direction of the particle. Initially, that particle is going which way? To the right, right? So we're going to say thumb to the right down here. My palm has to point upwards because my palm points in the direction of the force. And if it curves upwards from the bottom, then the magnetic force is upwards. So thumb, palm upwards. Which way do my fingers point? Into the page. So the magnetic field in this case would be into the page. What if you had looked at it at the top of the circle here instead of the bottom? Later we would say thumb to the left. Palm points downward in the direction of the force. Okay, fingers still point into the page. So it doesn't matter where you look at the position of this proton, you're still going to get the same answer for the direction of the magnetic field. Good? Stop me if I go too fast or any of these, okay? Number 9, this diagram shows a proton moving at 1.0 times 10 to the 5 meters per second through perpendicular electric and magnetic fields. What's the net force acting on this particle? And will the net force change over time? I like this question, actually. It's not really a cathode ray tube question per se, but I like the question. What's the net force? Well, there's two forces acting here. There's an electric force and there's a magnetic force. Okay, because of the electric field and the magnetic field. Which way is the magnetic force acting? The positive particle, let's say thumb in the direction of the particle, okay, fingers in the direction of the field, which is, because represented by a dot, it's out of the page. Magnetic force points, thumb, fingers, downwards. Let's label that. Yeah, it's the right-hand rule. Thumb, fingers, right palm points downwards. Yeah. So the magnetic force is downwards. Which way is the electric force? If the electric field is downward and it's a positive particle, which way is the electric force? Downward. The electric force on a positive particle is in the same direction as the field. If it was a negative particle, the force would be opposite to the field, right? Remember that? It's been a while, I know, but it's a good question. It takes you back to a couple units ago. It kind of forces you to revisit that stuff that you did a couple units ago. All right, we want to find the net force. Let's calculate the values of both of these forces. This one would be Q times E. This one would be QVB. Once we get the values of both of those forces, and I think they're both pretty straightforward to find here at this point, what would we do with them? We'd add them up. Because they're both in the same direction, we make them both either positive or negative. It doesn't really matter which, right? You just use QVB. I mean, if you get the answer in the back of the textbook using QVB, then their answer is wrong. Because if you're looking for the net force, it's got to be both of those forces combined, right? So whatever QVB is plus whatever Q times E is. Now, question B, this is a question that I really like here. Will the net force change over time? Yep. Well, let's find the magnetic force. It's a proton. So the charge is 1.6. 1.6 times 10 to the minus 19 times the speed of the particle is 1 times 10 to the 5 times the magnetic field, which is, what was it, 0.5 Tesla? Okay, so we got a magnetic force of 8 times 10 to the negative 15. Now let's add to that the electric force, which is 1.6 times 10 to the minus 19. Multiply that by the electric field, which is 100 newtons per coulomb. You get 8.02 times 10 to the negative 15 newtons. I'm sorry? Okay. We're good? Will the net force change over time, yes or no? Hogan? Okay. Will the net force change over time? Somebody else? Who says yes? Who says no? The answer is yes, it will change. Why? What happens? Yes. The strength of the field will stay, of each of those forces will stay the same, but the direction won't. The electric force will always be downward, right? But as soon as this changes direction, and it will change direction because there's two forces acting downwards on it. As soon as it starts moving in this direction, then what's the direction of the magnetic force? It's going to be thumb, fingers, palm points this way then, right? So if you got an electric force downward, a magnetic force that points this way, okay, you could add those vectorially, but they're not going to give you the same answers just adding them the way we did for question A. That make sense? So the values of the forces don't change, but the directions do. And if the directions change, we don't add them together in the same way, therefore the net force has to become a different value. And finally, question number 10. Suppose a passenger accumulates 5 microcoulombs of negative charge while walking from left to right across a carpeted floor, security gate at an airport. The metal detector at the security gate exerts an upward force on this charge. What's the direction of the magnetic field within the detector? Well, if the magnetic force is upward, okay, and the person with 5 coulombs of charge, positive 5 coulombs of charge, is walking this way, then what's the direction of the field? We'd say right hand. Oh, is it negative? Okay. So we'd say left hand. Left hand, thumb in the direction of the particle. Palm points in the direction of the force, okay, which is upwards. My fingers would point out of the page. So that would be the direction of the field, would be out of the page. If the whole security setup is the way that we have this drawn here, right? If the metal detector uses a 0.05 Tesla magnetic field, roughly how fast would the passenger have to run through the detector in order to feel weightless? I love this question. You want to run through a security detector and float or fly through the security detector? How fast do you have to run? Faster than the security guard chasing you, sure. We don't even know what the mass of this guy is, but here's the thing, it doesn't matter. Okay, let's pick a mass. I'm about 70 kilograms. Let's use my mass. In order to float, then there has to be an upward force equal to a downward force, right? Forces have to balance. The upward force is a magnetic force. The downward force would be a force of gravity. So we would say a QVB equals m times g. V is equal to mg over QB. Let's say 70 times 9.81 divided by, what do we got here, 5 times 10 to the minus 6 times 0.05 Tesla. Let's calculate that value now. We got 70 times 9.81. Suppose equals, let's divide that by 5 times 10 to the minus 6 times 0.05. How fast do you have to run? 2.8, 2.7. Well, I would have to run. Okay, I don't know about you. You'd be a little bit different, but I'd have to run 2.7 times 10 to the 9 meters per second. Is it practical? No, because that's 10. Because that's about 10 times the speed of light. That's my question, right? If you can run that fast, why are you flying on an airplane that can travel maybe 800, 900 kilometers per hour? Yeah, you could travel 1 billion. You can travel 10 billion kilometers per hour here. That's what that is. It's about 10 billion kilometers per hour. If you can run that fast, don't hop on an airplane that's, okay, unless you just want to brake. Don't hop on an airplane that's traveling at 900 kilometers per hour. Well, unless you want to make a point, yeah. I guess that's right. I can run so fast I can float like a butterfly through. Except you'd be going so fast that nobody would see you. Exactly. All right. Let's take a look at the next development here. So roughly 10 years after Thomson performed his cathode ray tube experiment that ultimately discovered the electron, a guy named Robert Millikan came along and said, you know what? I think I can find more. Thomson's discovered the electron. He's found the charge to mass ratio of the electron, but I think I can actually find the charge of the electron, and for that matter, the mass of the electron. So what did Millikan do in order to find the charge and the mass of this? He set up an experiment that you can see in the diagram on the left-hand side of this page. It's not all that clear, but I'll describe what's happening here. In essence, it amounted to this. He's got two charged parallel plates. Let's hook it up to a battery that looks something like this. That would make the top plate positive, and it would make the bottom plate negative. Over here on the side somewhere, he injects tiny little droplets of oil. Now, how does he do that? He takes what's called an atomizer, which basically amounts to like a perfume dispenser. You guys know when you spray perfume, it takes a liquid and turns it into really, really fine particles. Not particles that are the size of an atom, okay, but really, really small particles. We call it an atomizer because it's turning them into really, really small particles. Again, not atoms, but really small particles. Now, these oil droplets are going to have charges. And they're going to have charges because they're going to be rubbing against each other, and they're going to be rubbing against the nozzle of the atomizer itself. So now what you've got here is probably hundreds of oil droplets in between these two charged parallel plates. Hundreds of oil droplets that are charged. Some of them are going to be charged positive. Some of them are going to be charged negatively. Make sense? What I want to do first is look at the ones that are charged negatively. Okay. We'll take a look at the ones that are charged positively in just a few minutes. There are two forces acting on these oil droplets that are charged negative. What are those two forces? There's, two forces, yeah. What are they? You got to know one right off the top, guys. Look at the picture. There's two charged plates with a positive charge in between those plates. There's going to be what kind of force? An electric force, right. Which way is that electric force point on the negatively charged particle? The opposite direction of the field. The field is this way, right? So the force is going to be upwards, right? And you don't even have to necessarily look at the field. Okay, we know that the negative particle is attracted to the positive plate, right? What other force do we have acting here? Sorry? Gravitational force, and it's going to act downwards on this oil droplet, right? Some people at this point ask the question, well, what about the cathode ray tube? When we did the cathode ray tube, we didn't pay any attention to gravity whatsoever. But now we are? Yes, that's right. We didn't pay any attention to gravity in the cathode ray tube because we were dealing with electrons. And there is a force of gravity on the electron, but it's so small that it just doesn't matter. Here we're not dealing with electrons. Here we're dealing with oil droplets. And oil droplets still are very, very small mass, but much, much more massive than an individual electron. The force of gravity is now significant. It now matters, whereas it didn't in the cathode ray tube. We could have paid attention to the force of gravity in the cathode ray tube too, but we still would have gotten the same answers because that force of gravity was so minuscule. Now it's not. All right. I want to look at this particle for a second. These charged particles that have an electric force upwards and a gravitational force downwards. If those two forces balance, and they might for some of the particles, for some of the oil droplets, they might not for other ones, but if they balance, then these oil droplets are either going to be suspended or traveling at a constant speed. Okay, forces balance. Things have to either be at rest or moving, but moving at a constant speed. In other words, not accelerating. For those particles, we're going to say Fe equals Fg. Don't mix this up with the velocity selection chamber of the cathode tube. It's not the same thing. That was Fe equals Fm. This is Fe equals Fg. The electric force equals the gravitational force. Now, sometimes we may not have the value of the electric field. So sometimes we may need to actually replace E with delta V over delta D. You guys recognize that equation? E is equal to delta V over delta D. That's the electric field between parallel plates, right? We learned about that in our second unit. In either case, we're going to rearrange and solve for Q. Okay, either rearrange this equation to solve for Q or rearrange this equation to solve for Q. What have we just found? Once we solve for charge here, what have we just found? Charge, right? Charge of what? Charge of an oil drop. Not the charge of an electron, the charge of an oil drop. A single oil drop. Go back to the diagram for a second. There may be hundreds or even thousands of oil droplets in there. We've found the charge of one of them. So what do we do after we've found the charge of one of them? We repeat the experiment. We repeat it again. We repeat it again. We repeat it again, hundreds of times, so that we get the charge of hundreds of different oil drops. And what do we find? We're going to find that the charge of each of these oil droplets is either 1.6 times 10 to the minus 19, or 3.2 times 10 to the minus 18, or 9.6 times 10 to the minus 17 coulombs, or 1.6 times 10 to the minus 18 coulombs, or 4.8 times 10 to the minus 19 coulombs, or so on. All of the charges that we will find of all of these different oil droplets will either be this smallest number or a multiple of them. Notice if we multiply that by 20, we get this. If we multiply it by, what would it be? 600, no, sorry, 60, no, 600, we would get this. If we multiply it by 10, we would get this. If we multiply it by 3, we would get this. All of the charges of all the different oil droplets are going to either be 1.6 times 10 to the minus 19 coulombs or a whole number multiple of that. What's his conclusion that he draws from that? There is what we call an elementary charge. There is a charge that is the basic smallest charge that you can have. You can't have anything smaller than that. 1.6 times 10 to the minus 19, the elementary charge. Which, by the way, will also correspond, since we've just discovered electrons 9 years before that, it will also correspond to the charge of an electron. So Thomson discovers the electron in 1897, finds the charge to mass ratio, and then Millikan comes along about 9 years later and discovers not the charge to mass ratio, but the actual charge of the electron, and the charge of any other fundamental particle as well. The second conclusion that he drew here was that charge is quantized. What does that mean? Exactly. Well, it means that you can have the elementary charge, or you can have a whole number multiple of that elementary charge. 2 times that, 5 times that, 60 times that, 603 times that. But you can't have 294.3 times that. You have to have 1 elementary charge or 58 elementary charges. You can't have 6.38 elementary charges. Charge is quantized. There's an elementary charge, and there's a whole number multiple of an elementary charge. Just like people are quantized. You can have 1 person, or you can have 16 people, or you can have 38,114 people. but you can't have 8.3 people. People are quantized just like charge is quantized. Now, just as a little aside here, you can probably imagine, look, if we found the charge, if Millikan has found the charge, and we already know from Thomson that the charge to mass ratio of the electron is 1.76 times 10 to the 11. And you can imagine at this point that we could probably also find the mass of the electron, right? Given this number and this number. We give Thomson credit for the discovery of the electron and measuring the charge to mass ratio. We give Millikan credit for measuring the charge of the electron. Who would we give credit for measuring the mass of the electron? Both of them. Because really you need both of them, right? You need the charge to mass ratio and you need the charge in order to get the mass of the electron. Does that make sense? (15.3) on 763 says an oil drop of mass 8.2 times 10 to the negative 15 is suspended. Okay, so we're going to deal with problems in a minute here where the particles are not suspended, either accelerating either up or down. But for now, okay, all we have to be able to do is deal with problems in which the oil droplet experiences no net force. In other words, the electric force equals the gravitational force, and it's either suspended or traveling at a constant speed. That's what we've got right here. We want to find out how many electrons the oil drop has gained or lost. Here's the particle. We know that we have an electric field pointing downwards. We know that the force of gravity must act downwards. And if the force of gravity acts downwards, then the electric force must therefore act which way? Upwards. If it's going to be suspended, these two forces have to balance, right? Let's set the electric force equal to the gravitational force. Say QE is equal to m times g. Do you remember when we derived this equation, we said that sometimes we have to replace E with delta V over delta D? Do we have to do that here? Do we know the value of E? Sure, so we don't need to do that here. Let's just say Q is equal to mg over electric field. That's 8.2 times 10 to the minus 15. Times 9.81 divided by 1.0 times 10 to the 5 newtons per coulomb. Let's see what we get when we do that. 8.2 times 10 to the minus 15 times 9.81 divided by 1 times 10 to the 5. What do we get? 8.04 times 10 to the minus 19. How many electrons has the oil drop gained or lost? How many? A number. What do we do when we're looking for a number of something? The total divided by the amount for what? So let's take this charge, 8.04 times 10 to the minus 19 coulombs, and divide it by the charge of 1 electron. That's going to give me, I think it's 6, isn't it? 5? What is it? 5? 5.03. So in other words, it's 5, right? Experimental data can give me anything, but it's going to work out to be pretty darn close to a whole number multiple. We'll always round it to that whole number multiple here because we're looking for a number. You can't have 5.03 electrons. You can only have 5. Now, is it gained or lost? That's the tricky part of this one. Why do you say gained? Because it's a positive particle? How do you know it's a positive particle? How do you know it's a negative particle? Yeah, good. If the electric field is down and the force is up, then it's got to be a negative particle. And if it's a negative particle, is it gained or lost electrons? It's gained. Is that good? Let's take a couple of minutes and try to do one or both of these questions, okay? Page 763. All right, let's take a look now at particles that are accelerating. Now, those particles that are accelerating could include these negatively charged particles that we looked at before with an electric force upward and a gravitational force downward if one of the forces is bigger than the other. Okay, the particles that we've looked at to this point have involved both of those forces being equal, but it could be that one is bigger than the other, and therefore would accelerate either up or downward. But we could also look at a positive particle where the gravitational force is downward, but the electric force is also downward. Clearly, that one's going to accelerate. In both cases, as long as the charged particle is accelerating, we're going to say F net is equal to the sum of the forces, Fe plus Fg. Guys, remember this from Physics 20? This is really Physics 20, isn't it? F net is also equal to m times a. QE is also equal to, Fe is also equal to Q times E. And the force of gravity is also equal to m times g. So instead of saying QE equals mg, we're now going to say ma equals QE plus mg. Now you got to be careful here. When you solve problems, you've got to start plugging in signs, positives and negatives. But we're not going to worry about that until we plug in numbers. This is the expression that we're always going to use. When we need to plug in numbers, then we'll worry about what should be positive and what should be negative. Real quickly though, okay, if I was solving this problem right here, Fe would be positive or negative. We plug in the value of this to be positive. We plug in the value of this to be negative because it's downward. Okay, if we're looking at this one, Fe would be negative and Fg would be negative. Does that make sense? It's not that much harder than the last set of questions we did, where Fe is equal to Fg. It's just that now we got to pay attention to signs, and we didn't have to worry about that before. Take a look at one example here, and that'll be it for the day. A tiny plastic sphere of mass 8.2 times 10 to the negative 15 kilograms is placed in an electric field. It has 10 excess electrons. Is the sphere going to accelerate, and if so, in which direction? Okay, let's assume that it does accelerate. Okay, we don't know that it will, but let's assume that it does. Okay, let's find out. Has 10 excess electrons, so its charge is going to be negative 1.6 times 10 to the minus 18 coulombs. There is an electric field downward. That means the electric force will be upwards. Why? A negative particle experiences a force opposite to the direction of the electric field. Force of gravity will be downwards. Again, we're going to assume here that it's going to accelerate. We don't know that that's the case, but if we're wrong, we'll find out in just a second. If we're wrong, what are we going to find the acceleration to be? If it doesn't accelerate when we think that it does, A will be equal to 0. So let's find the acceleration. If it's 0, then it doesn't accelerate. If it's not 0, then it does accelerate. M times A is equal to Q times E plus M times G. The mass here is 8.2 times 10 to the minus 15. Let's solve for A. QE is 1.6 times 10 to the minus 19. Remember, we always drop the sign of the charge. E is 1 times 10 to the 5. Let's leave that term positive because the electric force is upwards. Even though the field is downwards, the force is upwards. The force of gravity is 8.2 times 10 to the minus 15 times 9.81. For this one, we're going to stick a negative in front because the force of gravity is downwards. Now, I don't care whether you put the negative in front of the 9.81 or in front of the term. It means the same thing in the end. Yep. This charge? Yes, because it says it has 10 excess electrons on it. What have I said there? Oh, good. Yeah, you're right. You're absolutely right. That should be 10 to the minus 18. No. 10 to the minus 18 coulombs because that's the charge of our oil droplet, right? Not the charge of an electron. And it doesn't need to be negative 1.6, even though the charge of the oil drop is negative 1.6. We always drop the sign of a charge when we're plugging into an equation, right? Same as, that hasn't changed from way back and near the beginning of our electricity unit, that hasn't changed. Let's calculate this now. Let's make sure we can get it here. We're going to say 1.6 times 10 to the minus 18. We're going to multiply that by 1 times 10 to the 5. Okay, that gives my electric force. Now let's subtract from that gravity, because gravity is a negative value because it x down. Brackets 8.2 times 10 to the minus 15. Multiply that by 9.81. Now we get the right-hand side. Now let's divide by 8.2 to get the acceleration. 9.7. Does it accelerate? Yes. Which way does it accelerate? Which way? Down? How do you know it's up? Because it's a positive acceleration. Good. We can determine that it's a positive acceleration, therefore we can determine that it's accelerating upwards. If it was a negative 9.7, then it would be accelerating downwards, right? Good? We're good at that? Okay, what's your homework? Your homework are the practice problems on page 763, the ones that you were working on, and the practice problems on page 764. That's it. Okay? Work hard on these tonight. Let's come in tomorrow with some intelligent questions if we have questions, or ideally, you just get them all, and we don't have to go over it. Okay? Have a good night, guys.